Thank you again, Joe, for this opportunity to talk about our experience with the NIST GRASP performance test bench. We are very happy to share with you this experience. So for those of you who do not know me, my name is Lionel Birglen. I'm a full professor at Polytechnique, Montreal in Canada. I will be presenting today with Xiaowei Shan. She's a former postdoc in my lab. So this presentation was a little bit complicated to orchestrate as I'm currently on a sabbatical leave in France. Xiaowei is now back in China. So none of us are in Canada at this moment. So I would like to apologize beforehand if the navigation through the slide is a bit difficult and it's not as smooth as it could be. I'll be doing the introduction part and also the conclusions, but the middle part, the most interesting one, will be done by Xiaowei, since she is the one who has worked extensively with the NIST test bench and has replicated the procedures in our lab. So before coming to this technical aspect, I would like to start the presentation with a few words about us. Don't worry, I have very, very few slides about that. I have no intention to bore you to death with presenting our own work for 20 slides. But we are from Polytechnique Montreal. It is the largest French-speaking engineering faculty in North America. Yeah, probably also because it's one of the only French-speaking engineering faculty. We are far less well-known than McGill and Waterloo and UBC, but actually we're not that bad. And if you look at the research budget, we have the second largest, just behind U of T for engineering. So we're actually pretty active on research. And we have now more than 250 professors, only engineering professors. So as a Canadian member of a Canadian institution, I cannot not show you a picture of our buildings under our beloved snow. So there it is. This is our newest building in Montreal. And a few words about my group. Our main expertise lies with underactivated robotic hands. And well, I don't think I need to explain to you what it is. As the Japanese say, you don't preach the Buddha. You all know very well, as much as myself, what is underactivated grasping. These are a few examples of prototypes we've developed in the past, ranging from the very, very small for surgical application to industrial size ones. One word of warning, maybe. We are robotic hands designers, and we are mainly focusing on grasping. We do very little manipulation in any. We have dabbled a little bit with manipulation in the past, but that's not our force. And we don't do so much grasp planning. So this presentation has to be understood as coming from people who design hands and who design hands for grasping. So this has a strong influence on what we have been doing and how we see NIST test bench. Basically, to make a long story short, in 2016, we received a grant from the federal government in Canada to prepare for the commercialization of our adaptive finger design, which is here illustrated on the left. And at that time, we thought it would be a good opportunity to replicate NIST test bench and to use that to characterize our fingers. So this is the backstory of our replication of the protocols provided by NIST. And with that, I'll leave the virtual floor to Xiaowei to present the technical aspects. Xiaowei?
I'm very glad to join this webinar and share my experience with you. Okay, So basically, I'm going to introduce the test that we have conducted for the grasp strength and slip resistance of our adaptive robotic hands. First, according to the test benchmark from NIST, grasp strength is a kinetic measure of the maximum force a robotic hand can impose on an object. The test method is to measure the squeezing force on a cylinder artifact. As can be seen from the figure, this was quoted from the benchmark. The artifact example suggests the use of two single-axis load cells for one-dimensional force measurement. Multiple cylinder diameters should be used for the preload capabilities of a particular hand for various object sizes, as can be seen from the right-hand figures. Next. Here shows a data plot example in the benchmark of the total grasp force, namely two load cells through the mean grasp force were expected for each data set. Next. In analogy, our tests utilize the two artifacts in 2 and 3 inches, designed and built with multiple uniaxial load cells, as can be seen from the figure on the left. 3 load cells and the steel plate were mounted on the upper and lower cores, respectively. Actually, we redesigned the slip artifact a little bit because less load cells may lead to unbalance, while more load cells may not be able to touch the steel plate simultaneously, probably due to fabrication errors. The 3 load cell configuration avoids the problem, since 3 sensor tips define a plane that can always be adapted by the steel plate. The reason we use steel plate is to avoid the shear force exerted from the fingers, because shear motion cannot be constrained by the steel plate, but it does not affect the transmission of the normal force along the sensitive direction of the load cells. Finally, rubber bands were utilized to bond the 2 cores. The preload of the rubber bands can also be zeroed in advance. Next. The artifact using 3 load cells was calibrated with known weights. The upper core facing downward is screwed with the load cells. The sensing tips directly touch the steel plate, which is clamped on the table with an underlying wood board. The weights were measured with a precision scale and then added in a bag hanging onto the artifact. Next. This is the test result from the calibration. The figure shows the result for 1 to 22 kilogram. The direct linear regression result for all the 22 data points is denoted LC number 1. By perception, the 3 other linear regressions are more linear internally, actually. The mean value of the 3 slopes were denoted LC number 2 for an alternative estimation of the overall slope. Next. The mean forces measured from the load cells are compared with a commercial 6-axis sensor. In the first column with the artifact size, number 1 indicates the rep or power grasp, while number 2 represents the pinch or precision grasp. The results are comparable between those from the ATI sensor and from the 3 load button cells under the calibration method LC number 2. However, the result in LC number 1 is not accurate, which shows the importance of calibration in the artifact design with the load button cells. Next. Actually, we ended up usually relying on the version with the ATI sensor, but as long as the calibration of the load cells are verified, it is an accurate replacement to build an artifact with a relatively cheap load cells. We can see the comparison of the cost. There still remain some issues. First, calibration is important, as can be seen from the comparison table previously. Second, the half shells sometimes separate because of the bending moments from the fingers, and also because the fabrication are not perfect. The two fingers are not exactly symmetric, so there are also shear forces applied onto the artifact that sometimes shear the two cores apart. Moreover, sensitivity to the tilt angle is worrisome. For example, how to hold the artifact in the air before the finger grasp is a concern. Many manual holds cannot ensure the orientation and contact height, although we have the tilt sensor. It was found that orienting the hand horizontally instead of vertically in the benchmark and placing the artifact on the breadboard with a sponge below could generate much less fluctuated grasp forces. It is an interesting finding in our test. Last but not least, the PVC waste pipes suggested in the benchmark were not conveniently available in Canada at that time. So at the end, we bought the standard PVC pipes called ASTM 1785 in Schedule 40 class from McMaster. Next. Okay, the next test benchmark we have tried is for the slip resistance. It is defined as a kinematic measure of a robotic hand's ability to resist a slip. The focus of this metric is to investigate the inherent surface friction properties of the hand. There are three steps based on the figures. First, place a cylindrical artifact in the robotic hand using a wrap grasp at maximum power. Second, pull on the pipe at a controlled rate of increasing force, recording force until gross slipping is visually confirmed between the hand and the PVC pipe. 3, repeat this process over a range of standard PVC diameters that the robotic hand is capable of grasping. Next. This figure shows an example test in the benchmark. It was conducted by commanding a fixed robotic hand to wrap around the standard PVC waste pipe. The common trend in the test was that the pull force increased almost linearly before reaching a peak force, and then yield a sudden drop in the pull force. The selection of spring, I think it's next page. Yes, the selection of the spring and linear actuator is very important for the control of the load rate. Next. In our replica, a linear stage provides incremental loading on the pipe through the fishing lines. The fishing lines are attached to a S load cell and the L bracket, as can be seen from the left figure. The load rate is decreased using an inline spring. The measure of interest in this test is the maximum obtainable pull force under grasp. The test was conducted under a nominal 6-bar pressure by the pneumatic actuation. On the right side, we can see the corresponding test results of some different configurations. It is not exactly like in the benchmark described that there's a sudden drop. Sometimes there's just a gradual change after the pull force reached its maximum. So it's another interesting finding. Next. This figure on the left side, we used this setup also to measure the pull-up resistance of various configurations, in addition to wrap and pinch grasping. Especially, you can see from the lower left side, the pull-up configuration of a robotic hand was illustrated. The corresponding test results are also shown in the right-hand figures. Because for the pull-out test, the artifact dropped out of the hand, so there are some very sudden drop in the force. in the test results. Next. These are the components we used for the test setup. Still, a few minor issues remain for further consideration. First, the test results can be quite variable for power grasps. We suspect how the object is placed in the hand is one of the culprits, because sometimes, if we put the artifact directly onto the hand, after grasping, the initial impact may lead the artifact into another orientation. And if manually hold the artifact, the height and orientation can also be tricky. So there comes the variety of the power grasps in the test results. Besides, the spring stiffness and load rate must be selected in accordance to each other for repeatable results. This is also after trial and error, we found that the load rate need to be very well considered, combined with the purchase of different springs and the stroke range of the linear actuator we purchased. In addition, the travel range of the linear actuator is related to the expected pull-out force and spring rate, as explained just now. Finally, we had alignment trouble sometimes when the pipe reached its end under grasp. But generally speaking, the test setup works very well as a low-force universal test machine. Yes, I think that's the end of my presentation. I would like to give back the presentation to Lionel for the evaluation of our robotic hands.
Okay, so thank you, Xiaowei. Actually, this last slide is just a video. So this is just actually a video showing exactly what Xiaowei described. So this is an example of the slippage resistance, the slip resistance test. So basically, we are putting the cylinder in the hand, and we are pulling progressively with the linear stage until slippage occurs. So you can see in the lower right corner, we have the real-time force sensing estimation by the S-shaped load cell at the linear stage. So at one point, very soon, I think slippage will occur, and you will see that also around the hand. You will see obviously the object slipping. There it is, and there it is. So actually, most of the time we found that when slippage occurs, it is not catastrophically occurring. What I mean is that the object slips a little bit, but the hand is still grasping it afterward, but with a much lower grasp force. So this is actually something we found occurring with many different settings, many different grippers and hands. So it's actually quite good because it makes the grasp and even the slip resistance quite safe, meaning you're not slinging a piece of PVC pipe around in the lab. This is the second test, well actually the first one we present today, the DeGrasse Strength. So you can see our artifact with the two 3D printed shells inside the PVC pipe. And the whole thing is held together with rubber bands. So this is actually quite simple. You put the whole thing in the hands and you close the fingers. Again, you have the real-time force recording, and we do this. I think in this video there's 3 grasp and release sequence. But typically we run the test, correct me if I'm wrong, Xiaowei, but 30 times, and we compute the average of the grasp strength, thusly estimated. So there's nothing really spectacular or fantastic to see here. But notice one thing: the half shells, they are oriented vertically. And this is sometimes a bit difficult to make sure of, which is why we use the tilt sensor also, sometimes just to make sure that we have the right orientation with respect to gravity. So here is the final force profiles, and you can see that the average grasp strength we measured was around 150 newtons. Okay, so I'll go back to the normal slides. If you have any interest in that, you can actually see the YouTube video. Okay, I'll put this in full screen. Okay. All right. So in conclusion, I hope, Joe, can you confirm me again? You're seeing the conclusion slides, just to make sure?
Yes, we are. Yes.
Okay, fantastic. So in conclusion, we have used NIST proposed metric and test benchmark quite extensively these last 2 years, and we agree that they are very, 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 very useful to us, and they are key to making sure that we have some numbers that we can actually and confidently compare between several designs and several hands. In this presentation, we've shown you actually our gripper with our fingers, but also we've actually been using the same test bench for many robotic hands and grippers. Some from some other prototypes that we cannot show you yet, they're not yet published, but also some commercially available system. And what we're very happy about is that when we tested some of these commercial versions of robotic hands and grippers, we were able to find the numbers they put in the spec. So in the spec sheet, you have some numbers, sometimes, not always, but sometimes you have numbers for slip resistance, grasp strength, etc. And we were able to reproduce these results. So that gives us quite some confidence into the test bench proposed by NIST. Of course, as we say, there are still some recommendations we can make and would like to share with you based on our experience. You've seen the details in the slides before. What we also suggest is to maybe be more precise in the description of the equipment that is needed to conduct the experiments. For instance, what type of load cell, really. Maybe create actually a BOM, a bill of material for each benchmark, similar to what Stanford has done with the HAP kit. That would be very nice. Make sure that all the parts are easily accessible. For us, it was quite surprising, but the PVC pipe listed in NIST documents, they are explicitly said to be used because everybody can find them in any hardware store. Well, maybe in the US, but even up north in Canada, it's impossible to find them, and we tried. We contacted several shops and hardware stores, and none of them carry that. So in the end, we found the closest relative to this pipe from McMaster and from McMaster. The load cell we order for RoboShop, and RoboShop and McMaster, they ship everywhere on the planet. So that could be quite convenient to add links to detail respective items from their catalogs. As we said, for the slip resistance, for instance, we found there is quite you have to be quite careful when you combine the velocity of the linear actuator and spring rate. So maybe some additional details for some of these tests should be listed, like those. You can also provide some MATLAB and LabVIEW files, maybe have a GitHub host for this file and a CAD repository, like we suggest GrabCAD. We've been using it quite often these last years. That would be quite convenient to replicate the 3D shells, the half-cylinder shells. We're very happy that all the equipment was actually not very expensive. The most expensive piece of equipment we purchased was a table, and that was clearly overkill. We didn't need a 12-lab table to do that. Beside that, the linear actuator was actually also over spec. We could have gone with something cheaper, but we had the budget for once, so we spent it. But affordability is really something I think is important, because if to replicate the benchmark, you need $100,000 in equipment, I think nobody would do that. It would be nice, but maybe that's just a dream. But to have a different test bench in different labs around the planet, and to be able to compare the same hands and see how reproducible the results are, or alternatively, maybe we can have an online database of results. But I'm not sure about the legality of this, because maybe some companies, if you start putting some numbers for their hands and they're not happy about that, they might sue you. So I'm not sure this is such a good idea, but why not? In the end, we actually only used 3 of the 11 documents provided by NIST. We used the DeGrasse Strength document, the Slippage Resistance document, the Split Artifact document. We also investigated, but didn't really go deep into the grasp efficiency and the grasp cycle time. We did some experiments with them, but not enough to report them with you today. And it was not really necessary to characterize our fingers, so we didn't spend much time about that. But there are still many more documents to comment, so I think probably more people need to get involved. And basically, in the end, I think standardization can really lead to better hand design, at least for us. And maybe in the near future, we'll be able to close the loop. That means design robotic hands specifically to have good performance with NIST benchmark. But that also has a drawback. We have to be sure that the metrics are really good and that people are not just trying to get the best numbers they can, but in the end, that's not what is needed in practice to equip a robot. So that's the end of our presentation. Joe asked me if he could record this talk, which of course he could. And we are also happy to make this presentation available to anyone who wishes to download it. So here's a shortened URL if you want to go there. I can also send the slide to Joe if you want to send them to the group or put them online. We have absolutely no issue about that. So that concludes our presentation. Thank you, everyone, and thank you, Joe. Thank you to the people of NIST for this great effort. Thank you to the committee on robotic hands also for organizing this and sending the invitation to everyone.
Well, thank you, Lionel, very much for your presentation, and also to Xiaowei. It was a great presentation. We're glad that you had the time to really dive deep into these artifact designs and test methods. This is the kind of input we're looking for, as you mentioned, from many more people across the whole range of test methods that we're investigating right now. And we're also looking for ideas for other test methods. We want this to be a community-driven effort. And, you know, as hand designs emerge, there could be tests that are specific to new designs that we haven't thought up with the hands that we're designing. So I think that we really need to spread the word. Anyone who's involved in this conference call today can invite people to participate in this meeting. So with that, does anyone else out there want to comment on utilizing some of these tests that Lionel described today, or possibly even other uses of NIST test methods? I call them test method prototypes that are out there.
Hey everyone, this is Adam Norton from the University of Massachusetts Lowell. Thank you, Lionel and Xiaowei. That was a great presentation. We've been at our facility. We've also replicated the grasping artifacts using kind of two of the designs for the low cost and high cost versions of the split cylinder artifacts. So we've also been in the process of collecting a lot of data, and particularly to your last point of comparing data between different labs, I would be very interested in contributing to something like that. We have a lot of different end effectors in our facility, and could potentially think about ways to transport equipment between labs, maybe for interlaboratory experiments, things of that nature. So we're certainly interested in ways we could collaborate in that way. I agree that it might not be totally legal to, or maybe problematic to post test data in a identifiable way, but there have been other efforts, say for response robots using test methods where they essentially anonymize data and present the robots that were used to collect the data, but you can't correlate results to one manufacturer. Something like that might be at least a useful piece of evidence for how, just to validate that these test methods are producing useful data to some degree. So yeah, I'm definitely interested in ways we can share data in that way to really harden these test methods moving forward.
Mm-hmm. Adam, would you like to mention what your organization, the Nerve Center, is doing in general?
Sure. So yeah, the Nerve Center is a robotics testing facility based out of UMass Lowell, and we conduct a lot of research and generation of test methods and benchmarks for measuring robot capabilities. And with that, we are in the process of replicating and generating as many benchmarks as possible. For instance, these ones through NIST, starting to get our own YCB object and model data set, as well as test methods for other types of systems, including exoskeletons, response robots, mobile vehicles, and further into manipulation outside of grasping for assembly, human-robot collaboration, etc. So we've been building up our test bed of systems that we can use to help generate these different test methods and benchmarks. And we've got a variety of mechanisms for people to collaborate or use our services for testing.
Okay. Thank you, Adam. So we heard some interesting things today. That we've had discussions with Lionel over the past year or so regarding his testing. Sounds like we need to, and we do this with our assembly artifacts that we're working on, try to make them more globally obtainable, and we will work on that. Getting away from PVC pipe to something more standard. The important thing to do is to be able to replicate these tests so that if you're testing two different gripper systems or grasping systems, that you can compare results on performance and report these results long-term as maybe a specification. So with that, things that we do need to look at is specifying load rate on the strength test and slip detection test, load rate, and the spring properties to use so that everyone's creating a force rate at the same force rate during their test.
Xiaowei and Lionel, this is Carl. I have a few questions for you. What Joe was just talking about is the force rate. So you have the linear drive speed and the spring constant as the two variables there, but I guess you can combine them into one, so then multiplied gives you a force rate of sorts, right? And it sounds like you tested a few different ones. Do you have any intuition on what range of force rates we should aim for?
Hi, Carl. This is Lionel. Actually, I think we do, but I have no precise number off the top of my head right now. Maybe Xiaowei does, but I don't remember. But we had produced an internal report on the test and what results we end up getting. Sadly, we cannot share these reports with you because some of these results are actually linked to our gripper, our design, which we are in the process of commercializing with an industrial partner. So we're not sure what we can share or not. But
Lionel?
Shall we?
Yes, sorry, I just lost my connection, but I'm not sure how much you mentioned about this load rate.
Oh, very little, don't worry, very little. I just
okay.
the expert.
Actually, we didn't get like a standardized procedure to get a conclusion on the load rate, because it's usually depend on the force range of the fingers. We tested a variety of fingers. They have their own range of force, and also because of the different surface properties of the finger phalanges, the way it behaves during pulling out are also different. So there are several experience we had with the pulling force is that first when the artifact was very soon pulled out from the fingers, maybe we should change to a less stiff spring to decrease the load rate. Or if there are many slips in the force test results, that also indicate that the spring may be too stiff or the velocity may be too high. In our experience, we just tried different springs to find a good combination. Also based on the stroke range of our linear actuator, because that's limited. Our the force of the fingers, for example, the rigid ones and the softer ones, have very different force range. We need to consider that and get a recombination of the speed and the springs. I would be very happy if what's his name? Any other scientists can find out a good standard for finding out the combination of speed and the stiffness of the springs. I'll be looking forward to getting some result or having others to get a conclusion on that.
Right. Possibly, this is Joe speaking. Possibly, what this could equate to is that depending on the force capabilities, holding capabilities of a particular hand design, that there might be a few different combinations within the test method that you should test over as far as load rates to get a good picture of the properties of your hand. Because those load rates also, I assume, take into account the types of materials that you're using on your hands and how they react to the speed of the force loading.
Right. So I don't know if you had a chance to look at the touch sensitivity test, but that one calls for testing across different closing rates of your robot fingers and then measuring the forces transmitted. So in that same line of thought, maybe the right way to do it is specify a range of force load rates, and you test across a sub-selection or all the entire range of it to report your force numbers on them. And you'll have a maximum, I'm assuming, somewhere along the lines, but at least reporting across the whole range, you can see where you're weaker as well.
Yes, I think actually that's a very good idea.
And so if you specify it in terms of force per second, and then you can calculate out your linear rate times your spring constant. The important variable is the force per second, and then there's some flexibility on how you want to combine your linear speed and your spring constant to get that. So the other question I had is for alignment issues. Do you recommend then the use of a tilt sensor in the test method to ensure proper alignment?
Okay. From my experience, and keep in mind I've been doing far less experiments than Xiaowei, I did not use them. I basically only looked that the half shells were approximately with the right direction. But yeah, on the other hand, the tilt sensor we use, it's one piece of equipment that's very affordable. We use the one for orienting the blade in a table saw, so that's available in any woodworking shop for 20 Canadian dollars. So it's okay. Not a big hassle, but frankly, I didn't use it. So, but I had, I think, less trouble with the half shell separating than Xiaowei. So, okay. Xiaowei, you confirm that or comment?
Yes. Yes. Can you hear me?
Yes.
Okay. Yes, I agree with you. We didn't use that much the tilt sensor. At the very beginning, we used it to, do you remember that in the benchmark, there was also a test of like the 90-degree orientation of the artifact. But in our artifact, there's no, like, because there's no shear force like between the two cores. So this internal force actually does not exist in our artifact, so we didn't test that much into detail. But we noticed that we can measure like different angles to get some more information about the fingers or the robotic hand. These artifacts are uniaxial. In the ATI sensor, it's 6-axial. So we used the tilt sensor to measure different angles, for example, 10 degrees at a time. However, when it comes to 90 degrees, the two artifacts tend to split apart. And also, this kind of measurement doesn't give us a very sound result as used in the ATI sensor. So we just give up this idea. However, I would like to comment that the use of the tilt sensor is also pretty tricky, because when the fingers grasp the object, there will tend to be a shock. And if we put, you notice that we have a steel plate, so we can actually adhere the tilt sensor onto the artifact. But the initial shock of the fingers tend to make the prescribed angle shifted a little bit. So although we would like to adjust the artifact into the correct angle, this force somehow changed the initial configuration of the fingers, which is not something we would like to see. We would like to see the fingers like more symmetrically, so that we can get like a more standardized information about the grasp force. So my comment, I would like to conclude that a tilt sensor may be useful, but like a regular macro size seems to be cumbersome for this test. And how to hold the artifact initially is still something we need to consider.
Yeah, I mean, it sounds like the test that as it currently is has some sources of variability, which is why we recommended conducting a number of trials. And so maybe the low-cost solution is conducting a number of trials and then taking an average over your results to sort of filter out the sort of chaos there that's kind of hard to control in the alignment aspects of things. Just to confirm on another question I had, that you said robot shop serves internationally?
It's a robot shop, I think. Now you start to doubt. But yeah, it's
okay,
robot.
Okay, that's good. I mean, that's good for us to know. I think McMaster car has issues serving internationally, so we'll probably try to stay away.
In the past, I hear that was true, that McMaster had some issue delivering in Europe and everything. But from what I hear recently, that has been solved.
Oh, okay.
Although I didn't check. But if you look at their website, I did a couple of months ago, they say they're shipping internationally, no problem.
And you didn't see any restrictions on countries?
The only restriction we had, well, we're in Canada, so it's not that complicated to ship to us. But, we had some issue with screws, surprisingly. There were like a 300% special tax on certain screws imposed by Canadian customs to American screws for I have absolutely no reason why. But the PVC pipe, we had no issue getting them delivered to us.
Okay. One other company we've been looking at is Misumi. I'm not sure if you've used them.
We tend to use McMaster more than Misumi because, well, two reasons. The catalog of Misumi is much smaller than McMaster, and they are more expensive.
Okay. And I just had a final comment. So if I'm not mistaken, you determined that you could get sort of the same performance measurement results with the single axis force sensors as you can with the 6-axis one?
Correct.
Okay, good. Okay, that's all the questions I had.
Okay, thank you. Any other questions? We're kind of running out of time. What I'd like to do real quick here is, let's see. I'm going to share my screen. And can everybody see my screen with a slide showing, a PowerPoint slide for today's meeting?
Yes.
Okay. So again, thanks for the presentation. The next thing I wanted to talk about, I'll be sending out more information over the mail list for how to go about accessing these documents. But you can get to them from that website that I have listed here. I'm not sure if that's in the way here. Anyway, so we have two documents, NIST Special Publication 1227, Performance Metrics and Test Methods for Robotic Hands. These are where the tests come from that Lionel discussed today. And there's, I think, a total of about 10 tests listed there, plus the artifact design. And what we're doing, and there's also another special publication that we started, less mature in that we threw a bunch of different terminologies on there that I guess we tend to use here at NIST, as well as terminologies that come from an ISO standard on gripping and grasping. We tended to focus on more of the robotic hand type terminology in this document, but that's up for discussion also. Anyway, it's important that if we're going to use standardized performance tests, that we also talk the same talk and agree on a standard terminology for reporting results. So that is the very early stages of a document that we would like to start discussing with this community. What I'd like to do is for everyone to download these documents. They're in PDF form, and submit some comments before the next meeting on both documents. I set up a mail list for doing this, and I'll send that information around. In order to comment on each of the documents, I just asked that in the subject line you either put terminology or benchmarking. And that, obviously, that each of those relate to each of the documents, and that will just help us sorting them here on the NIST side. So try to remember to do that. So I'd like to say that they're due at the next meeting, so if you can, within a month, maybe take some time to look at these documents and provide some comments. And based on how many there are, possibly we could discuss them during the next meeting. The next meeting, I am shooting for approximately 1 month from now, first week in December, before the holidays start really taking off. And during that meeting, we have another presentation scheduled titled Development and Evaluation of an Adaptive Robot Hand for Robust Grasping and Dexterous In-Hand Manipulation. George, I'm going to hack these names, but Contodius and
that's right.
Dracos.
Yeah.
Say again?
It's my name is
Robotic.
Yeah,
anyway, great guys, I'm sure, even though they have tough names, from Georgia Tech. They're going to discuss their research work, possibly some benchmarking work that they've started. They've recently become interested in our benchmarks. Again, we'll discuss the SP comments. Does anyone have anything else they'd like to discuss? So look for an email from me shortly, probably by tomorrow on the next meeting. I just want to make sure the Georgia Tech folks agree on a date. And along with that, I'll send you the information for accessing this mail list. If you have any problems with it, please let me know, and I'll try to figure things out, because this is a new way of communicating for us. We just set it up, so please be patient. At that, I'd like to thank everybody for joining. Again, get some of your colleagues who are doing similar work involved in this group, because the more input we have, the better the end result is going to be. Thanks, everybody.
Quick question. Lionel and Xiaowei, is your contact information available in the download of that presentation?
Is Lionel's?
Yeah.
Actually, there's just our name and address, but I don't think I thought about putting my email address. Apologies again for that. But you know, there may be less than 20 Birglen on the planet. So if you type my name, you will find my email address quite easily. Sorry.
It's okay.
All right. With that, thanks everybody, and until next time, please read the special publications.
All right. Goodbye, everyone.
All right.
Bye.
Bye. Thank you.
Goodbye.
Goodbye. Thank you.
Bye.